we basically cracked open the ideas that underpin fusion in the sun last time. And I want to continue with that line today. I'm not going to add too much more to that, although I do think that there's a really interesting fusion possibility that's starting to appear in the literature right now called lattice-confined fusion. And I want to take a moment to look at that and imagine how it could be playing out in the stars. And there's one star in particular, there's a few actually, but one in particular that I want to highlight where some really interesting stuff is happening that seems like it's going to have to move our understanding of fusion in the sun a little bit at least. So that's a pretty cool story, and it will conclude our discussion of the liquid to gas. Well, the Greeks, I guess, thought it was a solid. The solid to liquid to gas to plasma, which is where we're at right now in the consensus model of the sun, to maybe something like a liquid plasma, which seems to be starting to gain some traction. And again, why do we care? Why do we care about the composition? All right? Oh no, I'm sorry, busted your cup. So it goes, man. I'm sorry. Does anybody grasp why it matters what the composition of the sun is? Why I keep harping about this? Yeah. It is cool. I mean, that's honestly, science is half about because it's good to know, right? We want to put some order onto our chaotic universe. In the back, yeah. Exactly, yeah. And what do we get when we understand functions? Yeah.
We get a general idea of what other stars are made about.
We do. What else? Fusion, right? Technology. This is really, really important. So most of our, so science in and of itself helps us understand nature, which, as you pointed out, is actually pretty cool. Because, from a psychological standpoint, understanding how things work is the bedrock of being a sane human being, right? If you look at people who have extreme mental disorders, they have a really hard time feeling secure in any environment because they can't make models that map onto the world that allow them to relax into the situation, right? And animals also suffer from this too. And I used the example of my cat, right? She's just always freaked out. There's a little noise in the corner of the room. The house makes house noises, freaks her out completely. But we're kind of like, no, like houses make noises. We have a model for it, right? This is important in and of itself. But perhaps most importantly, if we want to make huge leaps where we're actually able to harness the power of the sun on Earth, we have to understand the material basis of the stars themselves. And so it's not just about curiosity. It's also about making these massive leaps of engineering. And it's true that we have a pretty good picture of the basic fusion reactions in the sun, and we talked a bit about those last time. But there's almost certainly more to it, right? That's how science works. We're constantly updating our understanding of how these things work. And as I pointed out a couple of times, despite the headlines that you see, we're very far away from being able to sustain our civilization on fusion power, right? And we're using a model where we basically try to focus a lot of energy upon some plasma, some gaseous plasma, and we're trying to get back some power out of it, and it's slow going, to say the least, right? So there's some other possibilities for achieving that too, and it also why is it slow going? It takes a ton of energy. Think about the center of the sun. It's millions of degrees, right? How do you pull that off on Earth, right? It's not easy. And so the cool thing about some of the alternative approaches to fusion right now, like lattice-confined fusion, which is basically the idea that you basically squeeze simple atoms between layers of metals, right? And you put some pulse on the whole system, and you can crunch those atoms together in a way that doesn't require really high temperatures. Actually, they're doing these at room temperature, these reactions. So that's really exciting, and I think there's at least some evidence that would support the idea that this is perhaps happening in stars, some places, and so I want to talk about that. Cool, and then if you guys have been following the textbook, the second chapter that you're going to go through this week is about spectroscopy. If you took the class last semester, we did a lot of that already, so I'm going to kind of cruise through it a bit today, but feel free to stop me if I'm going too fast. Of course, spectroscopy, in other words, analysis of light, is all we have when it comes to astronomy and astrophysics, right? We're not going to go out and dig down into the sun anytime soon. So we have to make the most of this indirect analysis. And that's a really interesting challenge. And I guess we'll tear that apart a bit, and you'll see what I'm saying. Actually, we're going to get more into that next week, too, because it's such a big topic. So I'm going to finish up right now with the standard model of the sun. I want to just walk you through a little bit of the debate that sealed that paradigm into history for about 100 years. This was came to a head between these two guys, Eddington and Jeans, who were absolute powerhouses in astronomy at the time. They were basically the two biggest figureheads. And I mentioned Eddington was really, really famous because he brought Einstein to the Western world, right? He was an Englishman, and he took Einstein's German writings and ideas, and he translated them, and he put them out in front of the Western audience for the first time and really popularized it. He was the guy who went, after the special theory of relativity was published, and you don't have to know much about the special theory of relativity, but it does say that light should be affected by gravity in a particular way, right? In a measurable way. And Eddington mounted this huge expedition off into, the hinterlands, across the oceans, to go and basically take pictures of a solar eclipse so that he could measure the positions of stars right behind the sun. And he was able to actually demonstrate that the predictions of the theory of relativity were correct. And this was kind of blew the lid off everything. It made Eddington a really famous dude. It's kind of hard to explain, but he was something like if you squeeze together all of your popular scientists like Neil deGrasse Tyson and Brian Greene, Michio Kaku, all these people, you put them together. This was kind of Eddington at the time. His rival, actually, another astronomer who was very popular, was this guy named James Jeans. And Jeans was not quite as charismatic, right? He was a very cantankerous man. And you see these kind of rivalries pop up all the time. Another really good one, which I don't know that we'll get to dig into in this course, is Edison versus Tesla, right? Tesla was a very big man. He came up actually with the AC motor, amongst other things, radio transmission, wireless power. I mean, they were literally using Tesla's technology to power entire villages. This was crazy. The city of Bolinas, right outside of San Francisco, was wirelessly powered for some short amount of time. They have these huge transmitters that they had posted, these huge, massive antenna structures out in the ocean. You can still see some remnants of these outside of Bolinas. So the problem was Tesla was an absolute nut. He couldn't get along with people. He was very protective and paranoid. And Edison was kind of the opposite, right? He was a showman. He would put on these displays. He would have the public come out to theaters where he would demonstrate his technology. He really won the hearts of people over in a way that Tesla wasn't capable of. And I think that it's really important for you guys to recognize that the progress of science and the theories that are popular have as much to do with the people who present them as they do with the ideas themselves. And I encounter it all the time that people come to me. I encounter people all the time who have great ideas, but they don't work well with others. They don't know how to play with other people. And it's very heartbreaking to them because they're like, why does nobody care about my ideas, right? There's so much more to it than just having a good idea. And I think that gets lost a lot of times. All right, so let's follow up with the standard model of the sun. Let's finish that out real quick. So there's this concept at play at the heart of astrophysics where we're trying to explain basically why all of the celestial bodies are spherical, right? And it turns out to be this, the standard explanation, which I think is a perfectly valid explanation, is that there's a perfect balance between opposing forces, right? So there's an outward pressure in all directions, and there's an inward pressure in all directions. And you get something, at some point, there's an equilibrium established where it's perfectly squeezed, right? You can think about just taking, this is actually a really interesting experiment. So if you take your hand and you try to, anybody who does archery or shooting or something will realize this too. But if you take your hand and you try to hold it still, right, somewhere, it's kind of hard to do perfectly. But if you take your other hand and push against it, all of a sudden, it's a very stable platform, right? So the same kind of thing is happening inside of the sun. And, oops, I skipped a slide. Let me go back one. So the basic idea here is that gravity and radiation and, gravity is perfectly balanced by thermal pressures, radiation pressures, the gas pressure of this body, right? Because the temperatures are extraordinary, the atoms at the center are crashing into each other with extraordinary kinetic energies, right? They're kind of clumped in too fast to be, clumped in too close to really be considered moving that fast, but they're definitely vibrating in a way. And we call that thermal energy. We talked about it last time. So this is the basic model for not only why the sun is shaped the way it is, but for how all of the bodies are shaped the way they are. Now, there's weird exceptions out there, honestly. There's weird things that beg new questions. For instance, Ceres is a tiny little, basically a tiny little planet, but it's considered an asteroid. It's in the asteroid belt. It's very circular, but it doesn't have the mass necessary to sustain that equilibrium, that hydrostatic equilibrium that I'm talking about. So, people are still scratching their heads. And there's several of these bodies, right, that are too small. They're still spherical. What's going on? I suspect they have a very ancient history. They were probably much bigger at one point in time, and they've kind of been peeled away like an onion. So, but there are interesting questions out there about that. So building off of this model, there's some other interesting lines of evidence that have been interpreted in the context of this. One of them is these ideas of convection zones, right? Where you have, does anybody know what convection is, basically? Who could explain it to us? Awesome.
Convection is when basically warm air, it comes through, it cools, it sinks, and then it warms back up.
Exactly, yeah. So convection is all about when something's moving fast, it takes up more volume, right? And when something's cold, it takes up less volume, so that it'll be denser. It's going to sink. The warmer things are going to rise. And so when we talk about the granulation that we see at the surface of the sun, at the photosphere, we see these little convection cells. That's at least how they're interpreted. Something that's okay. So this is fundamental. There's also thought that there is convection. So the atoms are actually able to just directly collide with one another and transfer energy out to the surface. And then we have radiation also. But the main player in this is thought to be convection. Radiation pressure is pretty weak compared to the rest of them. And of course, this is the idea. Radiation pressure is kind of the sense. Has anybody ever been in like an IR sauna or something like that? Have you guys heard of infrared light, right? This is the idea you can warm yourself with rays of light directly. So light can actually transfer heat and energy too. And those are the three main pressures that we have going on here. There's also something else interesting that plays into all of this, which is that the sun it sort of rings like a bell. It has harmonics that appear as a result of it. And the study of this is called helioseismology, which is really fascinating. So these ideas of convection, seismicity, these are things that one would generally not expect to find in a gas, which is very interesting. So it is true that on Earth you can see things happening in clouds, right? So it's often brought up by astrophysicists that I've talked to, oh, well, we do see some of these processes, like we see seismicity. In other words, we see waves traveling in clouds on Earth. But the weird thing is that clouds are actually condensed matter. They actually contain molecules which have come down together. They nucleate. A cloud has to nucleate on either a piece of dust or an ice crystal, something molecular, right? We shouldn't expect anything like that in the sun, right? We're expecting things to be very, very atomized and ionized, right? They're under extraordinary pressures. So this is an interesting sort of rough loose end that's hanging out there, I think, and further deepens the mystery as to the composition of the sun. Of course, we can apply this helioseismicity, and folks apply it to explain sunspots as well, where there's essentially this whole convection circuit which is going on. the cold, the dark spots are cold and they're sinking, whereas the limbs of these spots, the outer portions of them, are bubbling up, and we get these warmer regions. Now, I didn't mention this before, but I think it's also worth pointing out. The standard idea for how the solar atmosphere is so freaking hot comes down to the idea that these sunspots are essentially these bundles of magnetic, they say they're like tangles of magnetic fields, but in all reality, they're atoms that are participating in these magnetic processes. And what happens is when they break open, they fling things like a slingshot. They fling material, atoms, ionized atoms, into the upper regions at extraordinary speeds. Yeah?
Are those sunspots next to these sunspots, like say on the left and hit to the top right?
Yep.
Little dark spots?
Yep.
Those like more sunspots?
I think this is just kind of, yeah, this isn't a great picture, but usually they appear in clusters or pairs, right? So you have an arcing of a loop of magnetic material, which has a polarity, so it has a north and a south to it. You can kind of think of them as the tip of like a bar magnet a little bit. So they appear like that, and the openings are regions from one polarity to the other. And actually that polarity is reversing every 10 years too, which is quite interesting. And people don't really understand that process at all, which is really something, and again, why don't we understand these processes? Well, it probably comes down to the fact that we don't really understand magnets. That's probably where it all starts at. And sadly, I don't have a whole lecture to do magnetism with you guys. If anyone's interested, I will talk your ear off about it after class or some other time. But magnetism is one of those things where we treat it as a known process. We have a great mathematical description of it. We can predict it really well. But in terms of what the actual surfaces of the atoms are doing to make this happen, there's very little attention being paid to it. But there's some ideas out there that are really cool. All right, so another piece of the puzzle, which is really fascinating, and this is something that Eddington really championed. This is really, when people started studying fusion as a concept, right? The question was, how does this fusion process lend itself towards the production of a continuous spectrum? Remember, the biggest and craziest thing about this entire science is that the sun generates a rainbow, a perfect rainbow, right? It does have gas lines on it because there's a lot of gas in the atmosphere of the sun. But how in the world do you get a continuous spectrum out of a gas, right? You can't do it on Earth. There's never been a demonstration of a continuous spectrum. The curve that you get out of the solar spectrum, that perfect black body curve, you only get it from hot bodies, really, and I mean like a particular kind of hot body, like soot-covered bodies that are perfectly absorbing and perfectly radiating the input energy that's given into them, the radiation energy that's given into them. So what happened was people, after they got into the idea of fusion, they started playing with how in the world you could use that process to justify the continuous spectrum of the sun. And this is what they came up with. The idea is that the photons that are, and we talked about some of the different high energy photons that are produced during the fusion reactions. But needless to say, there's a lot of light given off at the center of the sun. The idea is that the light bounces around from atom to atom within the sun in this region right outside of the core called the radiative zone. And it bounces around for something like millions of years. Okay? And what happens, what people reasoned back in the early 1900s was that it bounced around in such a way that it produced the exact spectrum of a black body, which is an interesting reach if you think about it. But they were able to justify it mathematically, and there are certainly possible explanations for how this could be done. So much so that this is pretty much the standard model for the production of the solar spectrum as it stands right now. Like I said, I think it's on the move. I don't know that that will be the story 10 years from now, but that is the story that's in your textbooks right now. So these photons bounce around. Of course, the neutrinos are really, really high energy pieces of, instances of radiation. It's often treated like neutrinos are particles. Photons are also treated like particles, right? So what's going on there isn't entirely clear. But those neutrinos can relay really easily. They can pass from atom to atom in a straight line, no problem, all the way to Earth. It's been a nightmare trying to detect them. And I think they were finally detected in my lifetime, certainly, but not toward, I think maybe only 10 or 20 years ago. Okay, so there you have it. This is your standard model of the sun. You got that core region where all of the fun stuff is happening, the radiative zone where all these photons are wandering around for millions of years. Then you have this convection cell where the thermal energy is being transmitted in a way that leads to these granulations on the surface. And you have the sun. You have the picture of the sun. This is the standard model. Okay, well, this, like I said, I've hinted at it a few times. This was essentially finally ratified back at the end of the 1800s, early 1900s, and it came to a head with these two gentlemen. So there on the left, you have Mr. Eddington, and you have Mr. Jeans on the right there. So Eddington really established this idea of radiative equilibrium. He built on some of the ideas of Schwarzschild. And Schwarzschild said this in 1906. He said, radiative equilibrium in a strong radiating and absorbing atmosphere will be established when radiative heat transfer predominates over heat transfer due to convective mixing. So this idea of radiative equilibrium sustained in the gaseous sun forms the basis of Eddington's treatment for the internal constitution of stars. And this is essentially how Eddington is able to produce the black body spectrum after establishing this idea. The strange thing about the concept of radiative equilibrium is that the sun isn't really in equilibrium, right? It's radiating heat away at all times. And remember, all of the black body experiments on Earth are done in equilibrium. The temperature of the material, the black body in which the object that you're measuring is enclosed, has to be perfectly at the same temperature with the body that it's measuring. So this was an interesting leap. Again, this is a little bit of a tragedy that we see happening today, where the people who study one thing don't necessarily talk to the people who study the other thing. And this has actually gotten worse and worse in modern times, because in order to sustain a scientific career in this day and age, you have to specialize to an extraordinary degree. This happens in medicine too, right? You probably noticed this. You go to the doctor, they send you to a specialist immediately, right? And the same things started happening in science too. And these fields don't talk to each other. So the guys who are doing the thermodynamics experiments on Earth with the black body radiation, they're not talking to the guys who are doing the astrophysics and studying the stars. And I think this was ultimately a bit of a tragedy. So now another thing happened too. I want to mention this, and we're going to talk about luminosity today. But luminosity is essentially the total radiative output of a star. And it's, as we'll see later today, it's very, very difficult to calculate because you have to factor in the distance to the star in order to do it. You can get the apparent brightness of a star just by looking at it. Okay, this one's brighter than that. And people have been doing that for thousands of years. When you want to actually figure out how much power is being put out, the actual luminosity of it, you got to understand the distance to that star. And that's not an easy thing to do, actually. However, Eddington published a paper right around the same time that he was doing all this stellar research, this idea about the way that the stars produce their black body spectrum. He published an equation that's called the mass-luminosity relationship. And the mass-luminosity relationship was super valuable because, as you can guess, if you were able to know the mass of a star, which is actually pretty easy to do, you just look at the gravitational interactions it has with other bodies. If you can do that, then you can get the luminosity out of it, and you can go back and forth together, right? So this was super valuable. The problem is the mass-luminosity relationship is a little bit of a nightmare, right? It's not a simple. Actually, did I put it up there? I did. Okay. So these, by the way, the little dot with the circle around it, that's our sun. And so everything is in relation to our sun. But if you look, there's this little alpha scaling factor up here, right? So it's not a simple relationship between luminosity and mass. you actually have to add this factor alpha into it, and alpha depends entirely on the type of star that you're looking at. So this is a massive theoretical leap where you're basically just putting a fudge factor in there so that you can kind of do what you want with it. As long as you group the stars together and you say, well, that star, I think it's the same as that star over there. They're basically compositionally similar enough, we'll put them in the same class together. And these kind of fudge factor introductions are very much avoided in theoretical physics as much as possible, but they're kind of inevitable at some point. At any rate, it's hard to overstate the importance of this equation. This made Eddington a superstar in the astrophysics community. And I think it's part of the reason that he won this debate with Jeans. So, Jeans did a lot of work, he in particular, with the way that light scatters, right? And explaining why our sky is blue, for instance. He had a big hand in that. But he was a cantankerous guy. He also advanced a cosmology which was called the steady state cosmology, which is in opposition. We'll talk about this later when we get to cosmology, but obviously, you're probably well aware of the idea that the standard cosmology right now revolves around a big bang, right? A creation event. Turns out that every civilization ever has had this cosmology, long before cosmology was a science. Actually, cosmology was not a science until like the 1960s, essentially, because that was when there was this heralded discovery of the cosmic microwave background radiation. Okay, before that, yeah. No. Yeah, it's a great question. Yeah, the difference between cosmology and astronomy is that cosmology concerns itself with the evolution of the universe as a whole, right? Which is an interesting presupposition, right? That the universe as a whole does evolve is baked into the science of cosmology, right? What's interesting, and what I was about to say, is that Jeans advocated a cosmology that was not evolving, right? There might be local evolutions, right? Like life on Earth, or planets come and go, stars come and go. But as a whole, he advocated this idea. Let me see if I can read it to you in his own words. He says, this type of conjecture, which presents itself somewhat insistently, is that the centers of the galaxies are of the nature of singular points at which matter is poured into the universe from some other and entirely extraneous spatial dimension, so that to a denizen of our universe, they appear as points at which matter is constantly, continually being created. So people fought for this after the cosmic microwave background radiation was discovered. In particular, Fred Hoyle was a huge proponent of this idea. And there was a number of other people that were working on this idea. Ultimately, the CMB was just too tasty, right? Here's the thing about the CMB. It is a perfect black body. It is like better than the sun. It had like the error bars on the measurements of this thing are out of this world. Now, the entire thing still rests, and this is why I'm really drilling home this compositional issue. The CMB is just an observation, right? We point a telescope, essentially all these were done on Earth originally, and a case can be made that they're still essentially done on Earth because even though they measure the CMB at a distance away from the Earth, they're calibrated to look for something that they saw on Earth in the first place. I don't want to get into the nitty-gritties of that, but this question still becomes, how does a gas, as we saw in the sun, produce a black body spectrum? And the answer, and this matters too when it comes to cosmology, because how do the cosmologists explain the CMB to us? They say that the CMB is the echo of all of these gaseous, the exact same process that we're talking about with this circuitous journey of the photons around the sun. It's the same process that's playing out at the beginning of the universe for the cosmologists, right? So if that process goes away and there's a new process that's invoked for generating the continuous spectrum of the sun, then the foundation of the Big Bang is also in trouble, right? So this matters more than it seems to matter, and there's a lot on the line for maintaining that paradigm, right? Paradigms don't like to shift. People have whole career, countless people have careers. Nobel Prizes have been given for this stuff, right? And it's actually one of the craziest Nobel Prize stories ever in terms of, I mean, the discovery of the CMB was wild. It was the observation of the CMB was published in a journal. The next article in that journal is explaining it in terms of being the birth of the Big Bang. I mean, it wasn't like somebody just published it and was like, hey, what could this mean, right? People already had it immediately, and they latched onto it. And I don't think it can be overstated that this idea of the Big Bang long preceded anything approaching science, right? People have had this idea in every culture. The Mayans had this idea. The Incans had this idea. The Mesopotamians, Babylonians, Sumerians, the Chinese, ancient Chinese, everybody knew, without a doubt, that the universe had a beginning and it'll have an end, right? Now, you might ask yourself, why? Why do people think that? And I can't tell you the answer, but I can tell you that we definitely have a beginning and an end, each one of us, and that's one of the most difficult things in the universe to wrestle with, and that everything that we concern ourselves with on a daily basis revolves around that concept, right? Birth and death. They're the most important events in your life, for sure. Whether it's your birth or death or your friends or your family, it's a really important thing, and it's almost impossible to reckon with, right? I mean, I don't know about you guys, but I remember when I first found out that I was going to die when I was like 5 years old, and I was pissed. I was like, really? Really? I'm going to like go through all this work, and I'm going to build myself into some self-sustaining, creature, and then I'm just going to die? Like, this is not fair, right? And so I think that in terms of the evolution of us needing to impose a cosmology, an order upon the universe, in order to order things, right? It's almost necessary that we treat the universe like we treat ourselves, and that what we see in the universe come back to how our own lives play out. And so regardless of whether there was or wasn't a Big Bang, I think that it is absolutely in line with what humans need to explain themselves to themselves. Yeah.
Isn't that kind of a fallacy? Because, I mean, the universe doesn't have, I mean, it's not like it has an obligation to act in ways that we're familiar with, if that makes sense.
Like, it doesn't have a goal or something like that.
Yeah. I mean, I think we tend to apply like personification to things like that.
Yeah, that's kind of what I'm getting at without like directly accusing the cosmologists of this. I do think that, I mean, it's an open debate, right? It's a very popular model right now. It rests almost entirely on this cosmic microwave background radiation, which rests almost entirely on the gaseous nature of the sun. That's why I care about it so much, right? And it's like, maybe it doesn't matter as much as fusion technology or something like that, which also depends upon this paradigm. Maybe that's probably a more practical way to look at it. But I think that it is important for us to understand our universe. For me, personally, I find the idea of an eternal universe very comforting. But somebody else might not, right? And so it's difficult to say anything with any certainty about that. But I can tell you cosmology was absolutely not a science until the cosmic microwave background radiation was discovered. So that's where we're at with all of this. Jean's ideas, pretty much everything that he came up with fell out of favor, both due to this rivalry with Eddington. I mean, Jean's was extremely critical of Eddington. He wrote this: all of Eddington's theoretical investigations have been based on assumptions which are outside the laws of physics. And actually, Einstein was a little bit skeptical too. Einstein wrote this in a private correspondence. He wrote, Eddington made many ingenious suggestions, but I have not followed up on them all. I find he was, as a rule, curiously uncritical towards his own ideas. He had little feeling for the need for a theoretical construction to be logically very simple if it is to have any prospect of being true. Let's see what Eddington has to say for himself. Eddington says, this was in his landmark paper that explained all of this business, which we just got done with on the previous slides. There are some physical laws so fundamental that we need not hesitate to apply them to the most extreme conditions. For instance, the density of radiation varies as the fourth power of temperature. The emissive and absorbing power of a substance are equal. The pressure of a gas of a given density varies as its temperature. The radiation pressure is determined by conservation of momentum, and these provide a solid foundation for discussion. And he's right about this. The problem is that these laws which he speaks of were only demonstrated in condensed matter solid bodies on Earth, right? All of those black body equations were developed with carbon-based absorbers in chambers on Earth, and no one was ever, and still no one is ever able to demonstrate a continuous spectrum from a gas, right? Not saying it can't happen, but it hasn't been shown, and people can't pull it off. I think that, well, we'll get to that. I'll give you somebody else's perspective who's more important than me. So, what happened was also that Jeans had this terrible idea that the sun powered itself through fission, right? And very shortly after he popularized this idea, it was discovered that the sun was almost entirely made out of hydrogen with a bit of helium. And of course, hydrogen and helium aren't fissile material, right? So they didn't find this. And Jeans was, he kind of retired into some sort of sad obscurity at this point, right? Because pretty much all of his best justifications were buried. Eddington was a massive superstar. The mass-luminosity relationship threw him into the stratosphere. And that was it. People moved on. And, you know, the cosmology that developed as a result, like I said, in the 1960s, very much depended upon this idea of this radiative transfer process that happens in the sun. And there you have it. That brings us pretty much up to the present day. However, there was a really famous, this is a very, very famous chemist, this woman Bogart. And she's a very prominent plasma physicist and chemist. And in her most recent review of the state of plasma physics at the moment, she makes this very interesting little comment here. She says, she's referring to the possibility that these plasmas are perhaps better thought of as fluids than as gases, which is really interesting. And she says, this also reminds us that the gaseous plasma model of the sun, which has dominated us for the past decennia, so many decades, and which soon might be decrowned by the rivaling new liquid model. Interesting. So what do they mean by liquid? What's the possibility? Well, we talked before about Andrew's model when they were first looking at the phase diagrams of gases. They were studying gases transitioning to liquids and so forth. They hadn't been able to achieve the pressures and temperatures necessary to observe what we now believe is a special state called liquid metallic phase, right? This is interesting. This is when you have the right amount of pressure and a lot of temperature, you can actually get these atoms to behave with some sort of continuous bonding interactions, right? They behave like a metal, but they flow like a liquid. And so we're actually starting planetary scientists a little more into this than the astrophysicists for good reason, right? The planetary scientists don't care so much about cosmology. They're not too married to this idea of the gaseous sun. The planetary people are now starting to imagine that the cores of big planets like Jupiter are able to sustain their magnetic fields because they have liquid metallic hydrogen at their core. This is really interesting when you consider the fact that Jupiter is basically a star that isn't big enough to turn into a star. It's the same composition, right? And actually, we're going to talk a little bit about brown dwarfs in general today, but brown dwarfs are essentially Jupiter-sized planets. They're often a bit bigger than Jupiter. I guess they're always a bit bigger than Jupiter. And they're capable of some really, really basic fusion, but not the kind of fusion that we would expect in a star. So all these paradigms are on the move. I think it's actually really, really exciting. There's also this matter of lattice-confined fusion, which NASA's starting to pick apart. And I really want to talk to the guy who wrote this paper. I think his name's Carl Sandifer. He's at the Glenn Research Institute. And I actually just wrote to him, but I haven't heard back. So the idea is, like I said, essentially that atoms can be sandwiched between layers, perhaps layers inside something like a liquid metallic hydrogen or something, and you can get the production of new elements in this way as well. This is not to say that there isn't the standard fusion going on in the sun that we were talking about before. There almost certainly is. But there might be other ways of doing it which would point back to a different phase, especially in the photosphere, right? The surface of the sun, which very much looks like some sort of molten liquid, right? And this is what people argued about when we went through the history. There's also this strange case of a few stars with anomalous spectrums. So this is one that I wanted to highlight. This is called Shibilsky's star. And Shibilsky's star is very strange because what they found when they look at the spectra of Shibilsky's star is that it has a number of these heavy and unstable metals which are found in the solar spectrum. And this doesn't make any sense because if you have a metal that only lives for 15 minutes, how in the world did it get there, right? How are you getting the production of these big atoms if they only last for 15 minutes? Because the standard story, which we ended with last time, is that heavy elements are not made in stars of our type, right? Our star is basically only fusing things up to helium, which is the second simplest atom. The big ones are made in these huge kilonova, supernova explosions of neutron stars, right? And we talked about how neutron stars are thought to be essentially, atomless, right? They're just goops of material that don't have atomic structure. They're so dense, they're so massive, that when they blow up, all of the little bubbles can turn it into bigger atoms and so forth. So this is the standard story for where we get things even as heavy as, iron, the bigger atoms that we see on Earth today. They all came from supernovas. That's the story. But Shibilsky's star is strange because there's clearly big metals being produced in Shibilsky's star. And people don't know what to do with that, right? So there's a number of hypotheses as to what's happening. Actually, some of the more popular hypotheses is that aliens are dumping their garbage there, right? They're like, oh, we got all this nuclear waste, let's just dump it in the sun, which I think is like not a bad idea, actually, if you could get past the, sticking a bunch of nuclear waste on a rocket thing and getting it off the planet. But and another possibility is that the stars incorporated through the standard mechanism, they incorporated supernova remnants, which were much heavier elements that have just been decomposing inside of the star. The kinetics of that are a little squidgy, and I don't think anyone's really made a convincing proposal for how that happens. But anyways, they're discovering stars that sort of indicate that fusion might be happening in ways that we wouldn't expect in our standard model. So anyways, I'm gonna move on from the story of the composition of the sun. We'll get back to it when we talk about cosmology, but this is some really cool food for thought. Maybe it's unsatisfying because there's no solid answers here, but that's what we should expect from science, right? We're always updating how we understand things, and we have to maintain this understanding that science is a work in progress. It's a living discipline, much more so than engineering, actually, right? We have airplanes that fly, more or less. You can fine-tune them, you can make cooler airplanes, but we basically know how airplanes work. We understand aerodynamics, right? Science isn't like that, though. We're never done with it, right? We can verify theories. We can verify theories to the best of our ability, but all it takes is one experiment that nobody's thought of to disprove a theory, or at least to say, hey, there's something else going on here. So science is always on the move, and that's what's really exciting about it, in my opinion, with respect to engineering. It's always changing. We're always subject to massive overturns, I mean, think about it. Darwin came up with this theory in the late 1700s, right? He didn't publish it until he was on his deathbed, essentially, because he was, so afraid that people would ridicule him and drive him out of town for it. But that was only a couple hundred years ago at this point, right? It became popular in the 1800s. And that's our standard model for the appearance of all of this diversity of life forms on our planet right now. I mean, you'd be hard-pressed to find somebody who had a good argument against the basic idea of natural selection. But that was completely unknown, right? That was a completely new idea just 200 years ago. And, I think that there's more of those to come. We have a tendency as we go through history to look back and see humans just like us who thought they knew how everything worked, and they were certain of it, and they built careers on it. And so this is bound to be happening for us as well. Any questions about the composition of the sun right now? All right, cool. So let's talk about light and how we understand what we're seeing from distant stars. So like I said, there's this concept of luminosity, which is really important. And luminosity is the benchmark for how much energy is actually being output from a star. That's how we can actually make any claims whatsoever about how, the internal composition, the processes going on inside of the star, whether it's, a neutron star or whether it's just a garden variety star like ours. Of course, temperature plays into that as well too, and we'll get into it. I went over this a lot last time, or last semester, but this is the basic principle of how radiation spreads out with distance, and this is really important. So both gravity and radiation obey this inverse square law, which is pretty easy to understand here, right? So if you have 4 rays going through this panel over here, right, and then you move 3 times that distance away, you square 3, right, you get 9. 3 times 3 is 9. So at that distance, you're going to have 9 panels, and you still have only those 4 rays. So it's going to dissipate in relation to the square of the distance away from it, right? I think it's really easy to understand with light like this. Gravity turns out to be exactly the same. And why that isn't entirely clear, right? Our model for gravity is highly schematic. It's very much based upon a mathematical understanding of describing how things unfold, but we don't totally have a material explanation for that. With light, it's a little bit easier to understand. So this is how light falls off, and this gives us a bit of information when we're starting to think about the distance, but it doesn't give us all the information. So the best thing we have here on Earth is we can measure something called the apparent magnitude. That's how bright something looks in relation to something next to it, say our sun, for example, right? In order to calculate the actual luminosity, we need to understand the distance, and we're going to play with how we understand distance, I guess, next Tuesday, next week. But let's look at a couple of different magnitudes. So the magnitude scale is really interesting. It was actually developed in the 2nd century BC by a Greek, Hipparchus. And he put up this observatory on the island of Rhodes in the Mediterranean. And he took all of these measurements of stars and cataloged their brightnesses. And then he basically made this idea up, which was that he would arbitrarily assign one of the stars a magnitude, let's say, of 1. And then some of the fainter stars, he would just go down the list. And he made 6 bins for them, 1 through 6. So the higher the magnitude was, the fainter the object, right? So 6 is fainter than a 1. Later on, in the kind of scientific revolution days, like let's say the really big industrial revolution days of the 1800s, people came back and tried to fine-tune this a bit. The problem was that, of course, they started finding stars that were much brighter than a 1, right? So what'd they do? Well, they just made the scale go into the negative world, right? This gets really confusing. It's kind of annoying. There's a lot of stuff like this that happens where, and especially you'll see this happen when we get to the stellar classification system, where it just makes no sense to us now. And instead of just rewriting it, we just went with it. And so you can see there, like the sun is like a minus 20 something, 26, 27. The moon is like a minus 11 or something. Venus is our brightest planet. -5. Sirius is our brightest star. Then there's the North Star, Polaris, and so on and so forth, right? I don't know about this naked eye limit, what that means exactly. Obviously, you can see them. I see, we're going down, right? Some people can see things that are smaller than others. There's people who claim they can see the actual waxing and waning of Venus, which is interesting. Okay, and then the Hubble can see things that are really, really, really faint out there, and I don't think they would have, if we would have put the James Webb on there, it's basically the replacement for the Hubble, it would have gone even further. So how does this work? What's the system? So people tried to map some sort of mathematical representation. How much brighter is a 1 than a 2? Like a magnitude 1 than a magnitude 2. And it turns out that following from the ancient Greeks, and trying to impose this system on their star catalogs, it's arbitrarily 2.5 times brighter, okay? And it turns out if you put this into a mathematical formula, it varies by the fifth root of the magnitude, okay? So you don't need to know that, but the idea is that it's somewhat arbitrary, although it is consistent across the board. All right. Now, what about temperatures? So to bring it back, here again is our nice black body curve, right? This is the spectrum, all the different frequencies you see, and their power, how much of those frequencies are showing through. And this dude, Wien, gave us this displacement law. It essentially says that as the peak shifts here, that the peak is going to shift in correspondence to the temperature of that body. And you guys see this when you go to pick out light bulbs at the store or something, right? They'll have a temperature on it, and that tells you essentially how warm it is, right? This is basic black body thermodynamics. But we use this in order to propose our classification structure. Now, the idea coming from your textbook, it says, the color of the star provides a measure of its intrinsic or true surface temperature. Now, there's a problem with this. Again, I can't overstate the importance of the black body research that we've done on Earth. The black body research on Earth concerns itself with solids, maybe liquids. The problem is when you start doing liquid black body research on Earth, some of the temperature is going into the convection. Some of the heat, sorry, not the temperature, some of the heat is going into convection, right? The molecules are moving around. That is not accounted for in the rays of the black body experiments on Earth. This is really fascinating when you consider that the standard astrophysical explanation for the sun is that it's bursting with convection cells, right? So almost certainly the temperature that we get off of the photosphere, we say, it's standardly set. The standard temperature of the photosphere is 5,500 Kelvin or something like this. That cannot account for the convection temperature as well. So all of this temperature information we get from the color of stars, it's only an apparent temperature, right? It can't tell us what sort of heat is being lost into other processes that are happening on those stars as well. And of course, heat's going to be lost in the fusion reactions if those are happening in the outer layers as well, right? If lattice confinement turns out to be a thing. But certainly convection is a well-acknowledged process that's happening in the sun. And there's certainly heat being lost into it, which won't be apparent in the sun. Actually, Max Planck, who gave us, who actually solved the riddle of the equation for this black body spectrum, how it is that you get the wavelength relationship to energy. He actually wrote this about it. He said, now, the apparent temperature of the sun, he could have said of any star, is obviously nothing but the temperature of the rays, depending entirely on the nature of the rays, and hence a property of the rays and not a property of the sun itself. Therefore, it would not only be more convenient, but also more correct to apply this notation directly instead of speaking of a fictitious temperature of the sun, which can be made to have meaning only by the introduction of the assumption that does not hold in reality. And how that was lost on everyone, I have no idea. But I assume that it has something to do with the embracing of the cosmology that results in this too. Remember, the entire cosmology of the modern world depends upon the sun being a gas, okay? And maybe it doesn't, right? Maybe there's another way to explain the CMB which is cosmological as well, but it hasn't been proposed yet if there is one. Okay. So here we have the color of some different stars from our cosmological garden. And of course, you can see that they range from this really hot blue, right? If you look at a flame, where's the hottest part, right? It's the blue. All the way down to something that's quite cool, like Antares here. And then our sun's kind of right there in the middle. It's a normal star. It's very regular, average Joe kind of star. And our star kind of peaks out at this sort of greenish yellow color. I would definitely say it's more towards the yellow. Actually, our atmosphere introduces a bit of the yellowing to it too, which is worth pointing out. So maybe it looks a bit greener out there in space. I wouldn't know. Let's see here. So again, when we're actually trying to look at the composition of the stars, when we're looking at the atmospheres, I know we kind of talked about this. We definitely talked about it last semester, but I want to make sure that this isn't lost on anyone. So what we do is quite simple. We split up the light that comes out into its constitutive frequencies, into its different wavelengths here. And what we see is a continuous spectrum, right? And when you have some sort of gas which is excited, you get these lines. When you put a gas in front of a continuous source, right, you can actually see that the gas is absorbing the light at the frequencies that it would be emitting them at. Remember, anything that absorbs must emit. If you absorb at some frequency, you must emit at that frequency as well. And that's why we can basically make this translation between these black bands and these colored bands and say that, okay, there's black bands on this star here. Those correspond to the emission lines, which we can observe in the laboratory here on Earth. And therefore, we understand the composition of the star. So, you know, hydrogen is by far the most abundant element in almost all of the stars. And, you know, the lines aren't seen, hydrogen lines aren't seen in some of the hottest and coolest stars. This really has to do with the state of hydrogen in those stars. It's often very ionized and it's not capable of reacting to light in the same way. So, you know, let's see here. Let's keep going. Gosh, maybe we'll even finish early today. How about that? So this is the spectral class that was set up. This is quite interesting. So originally, the astronomers back in the earliest days of spectroscopy, which was really only like the early 20th century, maybe the end of the 19th century, they started setting up this classification where they basically put everything in order of hot to cool. They ended up actually having to rearrange that. They dropped a lot of the different classes from it. And actually, there's a few more that have been added since then. But what's really frustrating, of course, is that the order of these letters is completely arbitrary at this point. It's completely divorced from any meaning for us. It just stuck, right? It's kind of like the magnitude scale. It just kind of drives you nuts that somebody wouldn't have rebirthed this a little bit. So what do we have there? Some of the strongest, you know, they based this on how strong the gas lines were that they're observing. So the strongest gas lines were called A stars, the next strongest were B, and then they got all the way down to O. And so when they went back and reordered them in terms of temperature, everything fell out of place and it stopped making sense. And instead of coming up with new letters, they just went with it. You know, it kind of makes sense, right? If you have a huge library full of literature where you're talking about O-class stars and, you know, you want that you want to be able to reference that in your next writing. And so you can see how we build on these mistakes. You've seen this happen like with the keyboard, right? Like, why is the keyboard arranged in the way that it's arranged? And it's a traditional thing, right? It was established that way because of the need to actually have typewriters function, right? And it's stuck. It's what we use today all over the planet is this QWERTY keyboard. But it's not really the fastest way to set up a keyboard. In fact, there's people who dedicate their entire lives to engineering cool keyboards. There's this crazy dude on YouTube who's just, his whole channel, I mean, he's got millions of followers. His whole channel is just dedicated to exploring new kinds of typing strategies, which is wild, right? But nobody's likely to adopt any of those anytime soon because we all already know how to type with the old one, right? And it's the same sort of thing that you see happening in science all the time too, and particularly in astrophysics. And I don't know if someone's going to come along like Martin Luther and just absolutely demolish this and demand that things get put back in order, but I kind of doubt it. So there you have it. That's the surface temperature ordering that we have today, which reflects what originally had to do with the strength of lines. Okay. There's more about that history in your textbook if you want to follow up on it. Now, recently, we've added some other spectra, some other classes into this schematic. And the ones that we've added here are actually brown dwarfs, which are really, I kind of hinted at them earlier, but brown dwarfs are some of my favorite astronomical bodies. Because a brown dwarf is essentially something that looked like it was about to turn into a star, but it didn't accrete enough material to do that. It didn't have the gravitational pressure to start that fusion reaction in its heart. And so what you have is, it's becoming easier and easier to detect these things, right? We basically detect exoplanets, I guess as they would be called, so bodies out there that are orbiting other stars. We've recently been able to detect them, and the way that we do that is we look for something akin to a shadow passing in front of the star, right? And so this is actually really new technology. We've, in the last, I don't know, I want to say 10 years, maybe it's longer, maybe it's less, but in the not very distant past, we've cataloged something like 5,000 of these, and we're only looking in one little direction towards one little part of our own galaxy, right? They're all over the place. The galaxy is teeming with planets. Many of them seem to be a lot like ours, right? And we talked a ton about this last semester, but some of them fall neatly into this brown dwarf category. They're huge in terms of mass, but their radius is comparable to Jupiter. And Jupiter in and of itself is quite an interesting case because Jupiter also gives off more energy than it receives from the sun. It is generating power by itself, and it's doing it through a similar mechanism to the Helmholtz contraction principle that was dethroned as a mechanism for powering the sun. So they're squeezing themselves, and there's a lot of heat generated as a result of that. So these are really fascinating, I almost called them creatures, but they're really fascinating bodies, and I think they play a potentially really interesting missing link role in between planets and stars. Because, it's not the purview of this class. We're not really going to talk about planetary formation. We did a lot last semester. Anybody who was around for that realizes that those paradigms are shifting wildly, right? I mean, we used to think that, especially like some of these planets, like the Earth is a really difficult one to explain. The Earth is 5 times more dense than the sun. Why is it not inside the sun, right? That's a really hard question to answer. It's the densest body in the solar system, right? Why is it not in the middle of the solar system, right? This is weird, right? And so there's evolutionary models that are coming online right now that are really starting to captivate people's attentions. There's this idea that Jupiter-like planets, or say Neptune-like planets that are mostly water and have rocky cores, that when we look out and we see solar systems forming, we see these things very close to the stars sometimes, and they're rapidly evaporating their atmospheres, right? They're cooking down into little rocks, right? And there's an interesting valley between the Earth-like planets and the Neptune-like planets where we can't quite see if there's a transition process going there. Are some of these Neptunes turning into Earths? We don't know, but maybe, right? So this whole paradigm for how these things form is on the run. And it's really, really starting to become interesting to think about stars and planets as on a continuum, perhaps. Maybe there's many different ways to make a planet, but certainly one way to make a planet is that it's almost a star, right? It forms maybe in its own sphere of influence, and then it's kind of swept up into the soup of of some sort of protostar's circumstellar disk, right? As it's forming, these planets are grabbed up. Maybe they were on their way to have their own solar system, but it didn't work out for them for whatever reason. So brown dwarfs are really fascinating. And they've assigned them, they essentially had to create a new piece of the spectrum for them. And here you have a couple of them. Jupiter's down there at the far cold end of things. It's only 125 Kelvin, which is quite cold. But it's not nothing. Then there's a few other brown dwarfs you can see. They're about the same size as Jupiter, but they're a lot hotter. And some of them have some very primordial fusion going on, which is interesting. What did I want to say about that? So what really is the difference between a low-mass brown dwarf and a high-mass planet? The IAU, which is the International Astronomical Union, has made the distinction to be deuterium fusion. So brown dwarfs don't sustain regular proton-proton fusion like we talked about last time, but they do have the ability to squeeze deuteriums together, which are this very heavy kind of hydrogen. So they're so close to stars, people. They're so close to stars, right? Jupiter is is almost a star, but not quite. And it has the same composition as a star. It's almost entirely hydrogen with a quarter of it being helium, just like a star. So this is really cool food for thought in terms of understanding where these bodies came from. And then, let's see here. One last thing I want to say. Oh, I got a couple more things to say. In terms of the colors and what's going on there, one thing we can, oh yeah, go ahead.
Just curious, say we develop technology to move planets,
Ooh.
crash a planet into Jupiter, increase its mass, is it possible?
That might be a disaster.
I'm
Yeah,
sure,
yeah.
Just, yeah.
I mean, the thing about, so there's a whole question there about the stability of the solar system in general. And it's a very precarious situation, actually. So all of the planets are in these beautiful resonances with one another, and that's what lends themselves to stability. That's what lends the whole system to being stable. So as one goes around, it pulls another one with it, right? And they're in these intervals. This one might go 2, this one goes 1. They form these perfect harmonies, right? And actually, the ancient scientists and philosophers were obsessed with this. They were like, the solar system is making music. Because these are the musical intervals. These ratios are the same harmonics that you would get out of a guitar string, right? You get a perfect fifth, right? Which I believe is a 2 to 5. Or you can get octaves 1 to 2. Yeah.
If a white dwarf is comparable in mass to the sun, yet the same size as Earth, but Earth is more dense than the sun, then is the white dwarf more dense or less dense than Earth?
A white dwarf that's the same size as the Earth?
According to the slide, the white dwarf is comparable in mass to our sun, yet the size of Earth.
Yeah. Yeah, we're gonna have to play with what white dwarfs are later. I think that's too big of a discussion to get into. They're very strange, anomalous things. But obviously that raises the density to an extraordinary level, and matter starts to behave not as we would expect, right? We're not looking at the same atomic processes as before. One thing that does tell us a bit about the size, because remember, we need to know the distance to these things in order to actually say anything about the energy output and the reactions that are happening. And the size plays into the distance, right? One thing that we do see is this pressure broadening phenomena. So something that is really big, the lines are going to be under more pressure, they're going to vibrate at more frequencies as a result of it, and you get these broader lines that come out in giant stars, right, with this extended photosphere. Another thing that we can look at is the Doppler effect. You guys are probably aware of this. Like an ambulance goes by, and as it recedes from you, the frequency goes down, the tone goes down, right? It's like woo, 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 as it goes past you, right? So the same thing happens with light. You're going to encounter more of these. You can see here. This is supposed to be a light source, and as it moves away from the observer, the observer is going to encounter less of these waves per unit time, and therefore the frequency is going to go down. So this matters for us because, say something's moving towards us, the entire spectrum is going to be shifted slightly blue towards the violet. And so we get some sense of the motion of these bodies as a result of it. That turns out to be really important. Here you go. You can see some of these shiftings going on. That turns out to be really important because we can get information about the rotation of the star as a result of it. If we can actually separate out one side of the body from the other, we can see this shift giving us some information about the actual spin of the planet itself, which is really cool. So, and this, of course, is going to result in a particular kind of line broadening, which is, theoretically able to be separated out from the pressure broadening. So that brings us up to the question of how we can actually figure out distances to these bodies, something that I want to deal with next time. Does anybody have any questions? Yeah? All right. Yeah.
So Pluto's considered a dwarf, but isn't in the solar system. Yet Jupiter, you're saying, is a brown dwarf?
No, Jupiter's not a brown dwarf, it's a planet, but the difference between a planet and a brown dwarf is a fine line. It's very arbitrarily ascribed, right? I think that it's really important to think about all of these bodies as potentially on a continuum, right? If you start to think about the stars and planets as being formed by similar processes, and maybe even having evolutionary processes. Look, here's another reason that I care so much about the Big Bang. This is interesting. Look, if the cosmology shifts from the Big Bang, let me back this up. Let me paint you a picture. Let's say that the astronomers realize that, you know what, the sun actually isn't a ball of gas, it's some sort of metallic hydrogen. Then they don't really have the mechanism necessary to explain the CMB in terms of gas from the early universe. If the early universe goes away, then all of a sudden, all of the bodies that we have here have an enormous amount of time to develop. All of a sudden, we can say, maybe Earth is much, much older than we thought it was, because all we can do with radiometric dating, all we can say is that the last time the Earth and the Moon were molten was 4.5 billion years ago. Most scientists will tell you that's the age of the Earth, but the truth is, all they can tell you is that's the last time it was cooked. So what if the Earth, this is just pure speculation. I'm just giving you this scenario, Nobody is going to agree with me about this. But what if the Big Bang goes away, then we have trillions of years to make some of these bodies. Then we have a situation where stars can actually evolve into things. Maybe stars, when they cool and die, they just go dark. Well, what happens when they go dark? We know a lot of stars don't turn into black holes or go supernova when they die. Maybe they just cool off and start to look something like Jupiter's, right? Maybe Earth is on that evolutionary timeline too. Maybe there's a whole evolutionary science of planets that we're just not able to access because we only have 14.5 billion years in order to pull it off right now, and that's not enough time. So I'll just leave you with that food for thought. You got one more question, yeah?
This is a little off topic, but how come the plural for dwarf in the context of stars is dwarfs when
That's a really good question. I have no idea. That's ridiculous. Yeah. Dwarves, but they call them dwarfs. Yeah, you're right. It's crazy. Anyways, guys, have a great week, and I'll see you on next Tuesday. Yeah, have a great weekend.